In this video, I'll show you how to test the integrity of the threads on your Model A engine block stud holes. This is a good test to run if you're having head gasket problems, if you have the head off for the first time, if you've had problems removing any of the studs, or if you know that any of the stud holes have helicoils or other previous repairs. The test I'm going to show you is designed by Larry Brumfield. Larry designed high compression heads for the Model A and sold thousands of them in the 80s and 90s. He developed this test while doing R&D for his cylinder heads. This test puts each stud hole under about 10,000 pounds of tension, which is about what the threads in the engine block will need to hold against when your head is torqued down and the engine's running at 2,500 RPM or whatever. Now, before we get started, this test requires the use of some unusual parts. It's very tempting to take shortcuts and use substitutes that you can get at your local store or that you have on hand already. If you do that, the test won't measure what you think it's measuring. You could damage your engine block. Stay tuned after the test procedure, and I'll talk a little bit about why it's not good to use substitute parts for this test. The first part you'll need is a block of steel. It's not expensive. This one cost me $1. But it might be hard to find. You can find these at metal recyclers that sell surplus steel or secondary steel. Now, if you don't get lucky and find the right size piece, you may be able to have the yard cut a bar to size for you. Now, this is 303 stainless, but just about any steel will do. It can be round, it can be square, but it needs to be from 1.5 to 1.75 inches in diameter or on a side, and it needs to be between 3/4 of an inch and an inch in height. So this one's a full inch in height. Now it should be smooth on the top and bottom, no bumps or ridges. The top and bottom faces should be parallel within about 1/1000th of an inch. You can check that by measuring with a micrometer at each of the four corners. If you get identical readings, then you know that the faces are smooth and parallel. Now if it's not smooth or not parallel, you should have one or both faces milled flat. I've got this face was pretty smooth. This one was all right, but it's the one that the nut is going to turn on, so I went ahead and had this milled flat, and that way I know that they are absolutely parallel. Now you're going to drill a 15 32 inch hole in the center of the piece. Now if you use stainless steel like this, remember, it's going to work harden as it heats up, so you need to use a specialized drill bit and make sure that your mill or press can go down to 250 to 400 RPM. If you go faster than that, it's going to harden too much as you go through it. Now this is the bit that I use. This is a Norseman Type 178-AG bit. It worked really well. This bit drilled this piece, worked great. You can order these bits from different supply places. They're about 12 bucks. Now the last thing that you need to do on this piece is chamfer all the edges so that there's no sharp points that could gouge the engine block or the stud that you're going to use. You can use a half-round needle file that'll do both the inside edges and the outside edges. The second part you'll need is a set of short studs. These are double-ended studs. They're made by Auveco, A-U-V-E-C-O, part number 9712. You can get these from online fastener retailers. Cost about $1.50 each. They're sold individually or in packs of 10. What's important about these studs is these are grade 8. They're plain finish, so they're not zinc. They're 7/16 14 by 3/4 on one end, just like the Model A studs, and they are 7/16 20 on the other end. Again, just like the Model A studs. Their total length is 2.5 inches. You need to buy a minimum of 7. You'll need 7 studs to test all 14 holes on one engine block. Now when you get the studs, check the threads, check them for straightness, roll them back and forth a little bit, make sure they go in a straight line. The third part you'll need for this test is a set of Model A head nuts. You can get these from one of the Model A suppliers, come in packs of 14. You're going to need all 14. The nuts need to be 7/16 20, and they have to be what's called high nuts. That means they need to have a minimum height of 0.43 inches. Now you should get the ones that are cadmium plated, not the zinc ones. Some of the vendors sell cadmium, some of them sell zinc. Don't get the zinc ones, get the cadmium ones. And I recommend you buy the full set of 14 because this whole pack costs $4. And that way, if you buy it all at once, you know that all your test nuts are identical. For tools, you're going to need a torque wrench with an 11/16 socket. You can see on my torque wrench, I've got a reminder to myself when I'm done with this to back it off to 10 foot-pounds. That's just good to, I recommend everybody do that, especially if you don't use these all the time. It's just so easy to forget. Leave your torque wrench at 55 foot-pounds and leave it for a few weeks or a month, and that's a good way to throw off the calibration. You're also going to need a little cap full of motor oil, and you're going to need a brush. The general idea here is that you're trying to simulate the force that the block would experience from a real cylinder head. To do that, you need a stud and a nut and a big chunk of steel. The steel stands in for the cylinder head. It spreads out the clamping force over as wide an area as possible. Before you get started, make sure that all your stud holes are clean. I've got a video on how to clean these holes. There's a link to it in the upper right. Don't proceed unless you're sure all these holes are clean. And the first thing you need to do if some of your pistons are up is you need to crank the engine around until all 4 pistons are down in the bore. And that way you won't be pressing on one with the spacer. So just crank it around till you get them down a little ways. They don't have to be all the same. Now, there are 14 stud holes in the engine block, and in this test you're going to use each of your test studs 2 times and each nut 1 time. And I like to line up the studs on these holes, this kind of W shape right here, and then you can move each one 1 time. This helps you to keep track of where you are. So you would test each of these, and then you would move this one out, this one, number 2, number 2, number 2, number 2, number 2, number 2. And then after you've moved each of those, then you're done. So that's a good way to keep track of where you are. Now, if you get interrupted and you can't remember where you were, it's okay to, you can either repeat one, do it again, or move it. It's okay to use the stud 3 times. It's not going to change the result too much, but 2 times is the best. Put the stud in finger tight. Don't use any oil or other lubrication. Now, if one side of your spacer is smoother than another, make sure that side's up. And put the spacer over the stud. Make sure you're not overlapping any valves. Now, brush a light coat of oil onto just the upper threads of the stud. Put the nut on finger tight. Now, these nuts have a washer face. So you can see here, this face is slightly raised, and the other face is not. It's smoother. So make sure that the face that is slightly raised is the face that's going down. So put that nut on finger tight. Okay. Now your torque wrench should be set to 65 foot-pounds. Give yourself enough rotation space that you can bring the nut all the way to 65 foot-pounds in a single smooth motion. So now torque the nut down until you hear the wrench click. Now right now, there should be about 8,000 to 10,000 pounds of force on these block threads. If they're gonna distort or pull out, you want them to do it now. The way to tell that they've become distorted is to try to take the stud out. Remember, unlike with a bolt, there shouldn't be any twisting force between the stud and the block itself. It should be a tension force only. So if you remove the tension, then the stud should come out easily, unless the threads have been deformed. So reverse the wrench and back the nut off all the way. You can already see this stud's just sitting there loose, so that's good. Remove the spacer, and then remove the stud. This is what you want. Okay, now this nut should go in your scrap metal pile. Do not reuse this nut. Or at least not for anything critical. We're going to take a look at the stud, and looks nice and clean. No metal shavings. We're looking at the hole. Hole looks good. You can't feel any kind of deformation or anything with your fingers. So this one's good to go. At this point, you're going to take this stud and move it to the next hole. Then you're going to go around the circle and do the same. Now, if you don't reach 65 foot-pounds of torque, if that nut just keeps turning and turning, now that's bad. Or if you're unable to back the stud out by hand, that's also bad. Both of those mean that probably a thread has pulled or distorted somewhere, either in the stud or in the block, and you're going to have to stop here and consult an expert. So, assuming your first hole passed, take that stud, move it down to the second hole, and repeat the whole procedure. Apply the oil, torque to 65 foot-pounds, and then back it off and check the stud. Once you do that, again, the second time, once you've done it the second time, put this stud in your scrap pile. Do not reuse it. When you're finished, make sure you clean up any oil that might have happened to get onto the block. Don't forget to back off your torque wrench when you're finished. All right. If you just came for the procedure, that's it. Go run the test on your own engine block. And my next video will be all about the pre-flight checks that you need to make before you install a new cylinder head. So once that's finished, I'll link to it here. However, if you're interested in some of the reasoning behind why this test has certain requirements, like not reusing the nuts, then come on back to the bench with me. I'm going to try to explain some of the reasoning. Here's something you may not know about fasteners. A grade 8 nut is softer than a grade 8 stud. While the tensile strength of grade 8 fasteners, the tensile strength is the same across nuts and bolts and studs, the core hardness is different. The grade 8 nut has to score 32 or less on the Rockwell C hardness scale, but a grade 8 stud has to score 33 or more. Higher is harder. So this means that whenever a grade 8 nut and a grade 8 stud are tightened against each other, the nut will always yield. This image shows a computer model of a nut tightening down on a stud. And here's your cylinder head surface right here. So when you tighten the nut, you're actually stretching the stud. A stud will stretch by sometimes more than 5/1000ths of an inch over its entire length as you torque the nut down on it. And when the stud stretches, the nut is jammed against the cylinder stud boss as the first few threads of the nut grab hold of the threads of the stud. Now you can see that the force isn't spread out across all threads of the nut equally. Instead, the bottom thread absorbs about 1/3 of the total load, and the second thread absorbs about 1/4, and the third about 1/6, and so on up. And you can also see how the nut is deforming radially. Here at the bottom, it spreads out as the stud is compressing it against the stud boss. And because the nut is softer than the stud, these bottom threads compress, and that compression changes their thread pitch. Now, when materials are compressed, they've got a tendency to stay compressed to some extent. So this means the threads of the nut will not return to the same pitch when they're loosened, even though the threads of the stud will tend to return to the same pitch after being in tension, right? So the stud is being stretched, the nut is being compressed. The pitch change isn't going to be noticeable to the eye, but it manifests as an increase in friction. So the next time that the nut is tightened, the friction is going to change. When you apply torque to a fastener, most of that torque goes into overcoming the friction between the two pieces. Only a tiny part of the torque goes into increasing the clamping force on the cylinder head. Now, if that friction increases because the nut threads have compressed and their pitch has changed, then the clamp load that you get from a given torque, from 55 foot-pounds or 65 or whatever you're using, the clamp load is going to be different because your nut, the thread pitch on this nut is different. That means you're not going to get the force on the cylinder head that you think you're going to get. All right, why you can't just use a washer? Now, you might have watched this test and wondered why, instead of fabricating a special spacer, well, why couldn't I just use some grade 8 washers stacked up? Look, I pulled these out of here's my personal collection. So look, here's a bunch of grade 8 washers. I got these nice big fender washers. Look at this. I got a nice big spacer here. I've got this cone spacer, right? So instead of making this, why couldn't I just stack these up, make a big fat stack? Surely this would disperse the force just the same as that. I mean, they're practically the same height, right? Well, it turns out washers don't really spread out the load like you think they do. So this is an image. This is pressure tape. This is the pressure that's recorded. First, you take a hex nut by itself, and then this is a hex nut on top of a flat washer. And you can see the flat washer only distributes the hex nut's force a tiny amount. Almost all the force is still being applied directly under that narrow ring where the nut is putting pressure. So even if you stack these up, you're still going to have a high risk of deforming the block face or the threads by applying all this force, not spread out, but right around the edge of the hole. Another issue is research that was conducted in the 1980s looked at the effect of having a washer, because washers are, you can see this is a 1/2 inch hole. So if I use this washer on this stud, you can see I've got a lot of play here. And if you've got a washer that is concentric to the axis of the bolt versus a washer that is eccentric, and as you torque down the nut, that washer is likely to move a little bit. When the washer is concentric, you've got equal loading between the nut and the washer faces, but if that washer becomes the slightest bit eccentric, in other words, off center from the axis of the stud, then your load actually really changes, and you've got a wide part of the washer taking the load here and a narrow part taking the load right here. And so that's gonna cause the load to be applied unequally. And if you're putting a lot of force on your block threads and it's unequal, then you may pull out some of the block threads because they're taking a lot more of the force than they should. Another problem is that if you stack up a lot of washers, even hardened washers, when you torque down the nut, some of that clamping force goes into compressing the washers, right? They're not completely rigid. So if you get a stack of, I got a stack here of 5 washers, spacer, right? When you compress these with the nut, some of that torque is going to go into compressing these washers. It's called embedding. A stack of 5 washers might compress as much as 1/1000th of an inch when torque is applied. And so some of that torque that you're putting on it is going into just compressing the washers together. And there's also friction as the washers are turning relative to each other. This further decreases the clamp load that you're applying to the block threads. So again, you're not testing them the way you intend to. So why we don't like zinc nuts or studs. So here's a zinc stud. You can buy these at Advanced Auto Parts. Note that they look very, very similar. And you might be wondering, well, why can't I use zinc-plated studs or zinc-plated nuts if those are easier to get? And the reason is zinc plating has an unpredictable effect on the friction between the fasteners. Depending on how the zinc is applied, whether it's clear zinc or yellow zinc or exactly how they got the zinc on there, some zinc plating reduces friction relative to plain finish. This is plain finish. Some actually increases it. Whereas cadmium's coefficient of friction is very close to plain steel. So if you're using cadmium-coated nuts and plain finish studs, that means your test is going to deliver more consistent results. Another issue with zinc is it has a tendency to flake off under high torque, little microscopic pieces of zinc flaking off, which can increase the friction in the connection even more, especially if you're using a stud and you are reusing that stud a couple times during the test. First time you do the test, little bits of zinc are going to flake off. So again, you're increasing your friction. That means that the clamp load you measure the second time is not going to be the same. This is the stainless steel spacer that I used. After using it 14 times on each of these stud holes, you can see that the combined torque from all of those nuts has created a depression in it. I measured with the dial indicator. This is about a 0.02 of an inch compression. So this is a stainless steel. It's very hard, but you can see even with that hardness, after all that torque, you're still getting some compression of the piece here. And that's another illustration of why it's important on those studs and nuts not to reuse them over and over, because this kind of compression is happening on those pieces each time you do them. Thanks for watching to the end. I want to thank Larry Brumfield for his generous help in preparing this video. And also a big thank you to Shannon at Barron's Machine Shop, without whose Rockwell mill this video would not have been possible. Meanwhile, if you're an expert Model A mechanic, post a video yourself. Add to the library of YouTube. Doesn't matter what it is, simple maintenance tasks, anything. We need more good Model A instruction videos out there. Please share your knowledge with the world.